Okay, good morning, everyone, and welcome to a new edition of the Research Division Seminar. Today we have Boris Gänsicke, and it seems that many people is interested to know how the world will end. So in order to do a proper introduction of the speaker, I would like to invite Pablo Rodriguez here to talk.
Thank you, Jorge. So welcome, everyone. Good morning. It's my pleasure to introduce Professor Boris Gänsicke from the University of Warwick in the UK. All-time colleague, very good friend, and very related to the IAC for years. You know, we have a very tough, tight collaboration with the UK. Boris got his PhD at the University of Göttingen in Germany, was also a postdoc there, and then moved to Southampton University in the UK, where I got to know him, and I went with him. And then when I was settled in Southampton, the very missed and late Tom Marsh and Boris gave me a call. They say, we are going to Warwick to start a new group. Like, come on, just arrived in Southampton and you want me to move to Warwick. So we went there. I was the first postdoc. The three of us started the thing there. And now the group in Warwick is one of the most powerful in the UK. It's very, very big. I have to say that he's also been awarded 2 ERC advanced grants. What else?
That's all.
Yeah, that's all. We enjoy, hanging out together anywhere in the world. So, please, I hope you enjoyed the talk.
Thanks for the kind words, Pablo. It's always good to be back here, and thank you very much for the invitation. Very happy to have you all here and see all these interested faces to hear how the worlds will end, worlds plural. So I show this very nice picture and it will become clear what I'm talking about. The structure of the talk is split into 4 parts. I will first talk about the late evolution of planetary systems, and by that I mean what happens to planets around stars once the stars evolve off the main sequence. Then I will talk you through various observational signposts of such evolved planetary systems. And I will then move on and hopefully convince you that studying these systems is actually really useful in the terms of exoplanets in the broader context, because we can measure abundances. And then finally, I will introduce you to the latest statistics or results on detections of actual planets around white dwarfs. So let's begin with the first section and think about planetary systems. So it's only 22 years ago since the first planet orbiting a main sequence star was discovered. And since then, so much has happened. We now know that pretty much every star, when you look at the sky, every star has a planet, like within astronomical precision. That's probably a correct statement. And here is a artist's illustration of a planetary system. And if you look very carefully, then you see this is not the solar system because you've got water on the 4th inner rocky planet. But we think that configuration like this are probably fairly common. And so that leads then to questions. What's the future of all those planetary systems, of which we know thousands by now? And what's the future of the solar system? What will happen in the end to the solar system and to the Earth? And is there something we can learn from those evolved planetary systems? So let's just quickly have a look at where we are now. So the evolution of the sun starts here with star formation. We are now 4.5 billion years into the life of the sun. It's on the main sequence, core hydrogen burning, and eventually it will run out of hydrogen in its core, and it will evolve into a red giant, and it will become bigger in radius, cooler in surface temperature, and then it will lose about half of its mass in a planetary nebula. And the remaining mass of the sun, the burned out core, will shrink into a white dwarf. And that's what happens to most stars in the universe. They end their lives as white dwarfs. So here we are today, and this is the solar system on scale in solar radii. So we have 4 rocky planets, and we are currently here on number 3, the Earth. Then we have an asteroid belt, which is full of fragments of rocky planets, some of them fairly big. I may come back to that later. And then further out, we have giant planets, Jupiter, Saturn, Uranus, and Neptune. And there's a logic behind that, because those inner rocky planets, they formed close to the protosun, and volatiles weren't around to form giant planets close in. And then further out, beyond what we call the snow line, there's sufficient volatiles that a rocky core then can start to accrete and form a gas giant. So this is how the solar system looks. Let's wind the clock forward to about 5 billion years from now. So the sun is now a red giant, and it will reach a size which is roughly 1 astronomical unit in radius. And that means the surface of the sun, even though you should never talk about surfaces of stars, they don't have a surface, the surface of the sun will reach where we are here today. Now, if I flick back and forth, you notice two things. A, the sun becomes larger. B, everything moves out by factor 2. And the reason for that is that the sun loses about half of its mass. So its gravity weakens and everything moves out. And because the giant branch is a very long process compared to the orbital periods of the planets, everything just slowly moves out. And so we move forward. What happened? The sun has evaporated, definitely Mercury and Venus, and maybe the Earth. Whether the Earth can move out fast enough to avoid evaporation isn't quite clear, because it depends on when mass loss happens and the ratio of mass loss and the radius of the sun, whether the sun becomes sufficiently fast, big enough to evaporate the Earth or not. But that's totally irrelevant, because we will all be gone by then. And the important thing is that in the future, there will be a white dwarf, there will be one rocky planet, maybe two, there will be asteroids, so rocky bodies, and giant planets, okay? And so once we accept that, then we move forward and we say, well, we know thousands and thousands and thousands of exoplanets, and they orbit stars with spectral types M to about A, and so masses from like point a bit to about maybe 2 solar masses. And all these stars evolve into white dwarfs. And I cannot, for you, shortcut stellar evolution. They just move over here and become white dwarfs. White dwarfs are the burnt out cores. They don't produce any energy anymore. And so they're destined to cool along the white dwarf cooling track. So white dwarf enters the white dwarf cooling track here. It's hot and luminous, and then it cools down and moves in this direction. So second chapter is, how can we actually detect remnants of planetary systems? And so just because it's early morning, you're all bright awake. It's a question: when was the first observation that shows signatures of planetary systems apart from the solar system obtained? And I say obtained, not correctly interpreted, but obtained. What year? So this is audience participation time. Don't be shy. Yeah, Pablo is disqualified. No. Okay, so you're all very shy, but that's okay. So most people would say 1995, the discovery of 51 PEG B, radio velocity detection of a planet. That is not correct. And it's not 1992, which was the discovery of planets around a pulsar. It is actually 1917. Right. Before I show you the actual data, what do you need to know about white dwarfs for this talk? It's all on this slide. White dwarfs are small. They have about 0.65 solar masses on average, and they're Earth size. That means they have a very, very high surface gravity. And because of the very strong gravity, all the elements in a white dwarf are chemically stratified. So this is a cross-section through the white dwarf with the core, the center here, and the atmosphere up here. And this is a log scale. So 1% of the white dwarf is either hydrogen or helium left over from stellar evolution by mass, and 99% of the mass are the core carbon and oxygen, which is kind of the residual ashes of nuclear burning. And that means if we observe a white dwarf, so an observer observes the atmosphere and takes a spectrum, we should see either hydrogen or helium or a mixture and nothing else, because the heavier elements sink out of the atmosphere very quickly. Right, here's the data. This is a photographic plate. It's a spectrum of Van Maanen's star. Van Maanen was a Dutch astronomer working at Carnegie observatories, and he was studying high proper motion stars. And he took a spectrum of a very, very high proper motion star, and he noticed calcium H and K absorption line. So this the stellar spectrum is this trace in the middle, and then above and below are calibration lumps. And then he measured the parallax, and he found that this star is at a distance of 4.4 parsec. Now, calcium H and K are very strong lines in F-type stars, about 6,000, 7,000 degrees. And he measured the parallax, so the star is very nearby, and you have the apparent magnitude, which is something like 14, I think. And if you know the absolute magnitude and of F-type stars and the distance, it turns out this doesn't make sense because it's way too faint to be a proper F star. And his conclusion was he just discovered the faintest F-type star known. Now, what he didn't know, he discovered a white dwarf. It's the third white dwarf to be discovered, and it's also the third closest. Now, here you see a UV spectrum, calcium, magnesium, iron. And I said elements sync out very rapidly. So I have a little movie here, and that quite often goes wrong. Yeah, I fear that that might not work for some reason. Okay, so just to illustrate how rapidly metals sync out. So here's a spectrum of another star similar to Van Maanen. Gray is the data, red is the model spectrum, and all these features are metals. Now, this is today as we observe the star, and the other diagrams aren't so important. This one here is a little bit important. This is temperature. So white dwarfs, as I said, they cool, so they would move in this direction over time. And this is the calcium abundance relative to helium. And now I switch on gravity. There's a clock in the top right corner in millions of years. Watch that clock. And so as I turn on gravity, the metals sink out on timescales of about a million years. And I will try to stop the clock at about 2. Yep. So at 2 million years, this star actually looks very similar to the spectrum of Van Maanen's star on the previous slide. And then if I keep going, the metals disappear. And in a few million years, if our grandchildren observe the same stars, they wouldn't know that there were metals in the atmosphere because they have sunk out. This star is about 5 billion years old. So the metals disappear on like a fraction of a percent of the cooling age. Where do the metals come from? It must be external pollution. They must drop into the atmosphere and then sink out. Okay, so that was a big puzzle for a very, very long time. And the mystery slowly was solved in the late 80s, early 90s. And it took very long time to put together all the puzzle pieces. So Ben Zuckerman and collaborators at UCLA, they were pioneers in infrared astronomy. And they obtained a set of infrared photometry of a white dwarf. So this is the optical spectrum of the white dwarf. You see hydrogen lines. And then there's photometric data, and it shows an infrared excess. And they concluded that they discovered a dust disk or cloud around that white dwarf. Now, why would a white dwarf that is like 1 billion years old have dust around it? Wasn't clear at that time. But then with more modern instruments, this is a Spitzer spectrum. It turns out that it's not just a thermal infrared excess, but you see spectroscopic features from dust. And then if you know something about mineralogy, which I don't know in great detail, so the expert will tell you that the feature that you see is silicate dust, and not just any silicate dust. It's called olivine. So olivine will make that feature that you see in the infrared. And olivine, we have that on Earth. It's green sand on Hawaii. So you say, okay, why is there green sand going around white dwarf? So a seminal paper in 2003 by Mike Jura, also at UCLA, put those pieces together, and he said, well, if planetary systems survive and there's a small, say, an asteroid, and it gets a gravitational nudge, gravitational scattering, let's say, from a planet, say Jupiter, and it gets too close to the white dwarf, tidal forces, the strong gravity, will disrupt that rocky body, and it will eventually form a dust disk around the white dwarf, and the dust will then accrete onto the white dwarf and feed metals into the atmosphere, and that explains everything we see. So that's what we call the general framework of evolved planetary systems and how we detect them. So then the next thing is gas disks, and that's when I entered into this area. Accidentally, I was working on white dwarfs from the Sloan Digital Sky Survey. Pablo was probably still around in Warwick at that time, and we obtained beautiful spectra at the WHT follow-up, and we saw there's some funny feature here. If you look very closely, this is the calcium triplet, and if you look even closer, you see these are double peaked lines. Now, we work on compact binary stars, and if we see double peaked lines, we know there is an accretion disk. The reason is an accretion disk is a flat structure. It rotates, it emits, it's optically thin, it emits in emission lines, and so you get redshifted and blue shifted material. You integrate over the disk, visually, like you take a spectrum, it's an integral over the disk, and so you get double peaked lines. And we said, okay, there's a disk of metallic gas. There's no hydrogen, no helium, there's calcium, and then if you look very closely, there's emission of iron, and there's absorption of magnesium. So there's a gas disk around this white dwarf, and it turns out it also has infrared excess, so it also has dust. Now, scientists are curious, and so sometimes you just don't know what's going on. You say, well, we need more data. That's probably one of the most common statements you hear at conferences. So we thought we need more data. This is the WHT spectrum obtained in 2006. Nice double peaked lines, and we kept getting data, and we saw that over years, the morphology of these lines, and apologies, a little bit small, changes, and you can just skip to the bottom. And from a double peaked line profile, it now evolved that you have a sharp, strong spike at the blue shifted profile, and then a drawn out very long edge in the red. And so something is gradually, slowly shifting. And we thought, well, let's apply a technique that Tom Marsh and Keith Horn developed for accretion disks in binary stars, which is called Doppler tomography. Now, in a binary star, you see the disks from different orientations throughout the orbital cycle, which is a few hours. So within a night, you can get different sightlines across the disk, combine that into an image in velocity space. Here we have data obtained over more than a decade. We put that into the Doppler tomography code, and to our surprise, came out a very clean image. So what that shows is where the gas that emits calcium in calcium is located. The white dwarf is in the center. These are the kind of sight lines, dates of the sight lines, or the angles corresponding to the sight lines. And we see that the distribution of the gas is very non-axis symmetric, and you have a very bright, sharp concentration of gas around that white dwarf. Now, to illustrate how Doppler tomography works, I have a little movie here. So imagine you're the observer, and all you need to know is Doppler shift. You're up here, and the system you observe is down here. You take spectra over time, and material that moves towards you will be blue shifted. Material that moves away will be red shifted. And the spectrum you see here is simply the integral over everything that you have. And I will switch on the rotation of the disk and then see what happens. So as the disk rotates, the line profiles change. And at this moment in time, you have maximum blue shift. And now we have maximum red shift. And you see that this spike moves from initially maximum red shift to maximum blue shift and back. The period is about 25 years. So we originally only covered half a cycle, but by now we are almost through an entire cycle, and we see that that actually fully repeats. Now, putting that into context, debris disks and rings are actually very common. So here's a debris ring around Saturn. That's a Cassini image. And this is roughly to scale the disk around the white dwarf. And again, like the rings around Saturn are probably also tidal disruptions of small moonlets or small bodies. Now, moving on, studying that same star, we got absolutely amazing data from the GTC. We had 5 nights, and we got fast spectroscopy, so about 2-minute spectra continuously of that same star, the calcium triplet. And then we said, well, what the reason why we did that is just curiosity. We thought, well, if there's an accretion disk, disks usually flicker. So we expected to see some short-term stochastic variability, which might tell us something about timescales in the disk and so on. To our surprise, we didn't see any flickering, but what we did notice is, now Now I need to explain this diagram very carefully. This is the average spectrum across all data obtained in 2018. And then we subtracted from the average, we subtracted the average from each individual spectrum. And then we look at the residuals. And we found that there is a periodic signal in the residuals with a strictly coherent period of 123 minutes. And that same period appears in 2017 and 2018. It's the same period, it's stable over a year. And that means it's a clock in the system. It's not just some random blob in the disk going around or so. And so the only way we can explain a coherent period in these lines is that there's a solid body embedded in the disk going around in that disk. And we actually think this is a large chunk of whatever got disrupted that still sits in the disk. And because it is very close to the white dwarf at a period of 2 hours, it needs to have a very high density, at least 8 grams per cubic centimeter, to avoid being disrupted. Now, 8 grams per cubic centimeter is the density of iron. And so we kind of speculate, maybe this is a iron core of a planetesimal planet that got disrupted, the mantle and crust got lost, and the core survived because it's so dense that it can get quite close to the white dwarf without being disrupted. It's on a slightly eccentric orbit, and that orbit precesses because of general relativity, and that explains the 25 period that we see in the slow rotation of the emission line pattern. So that more or less all makes sense. And here's an artist's illustration. So here's the iron core of a planetesimal within the disk of its mantle and crust. And we do see things like that in the solar system. So here's a Cassini image of the rings of Saturn, and that's the moon Daphne, which is a remnant fragment maybe of whatever formed the rings. And it interacts with the disk, it opens a gap, and it causes some little distortions in the edges. So we think these disks around white dwarfs are probably way more complicated than just our cartoon picture of a flat dust disk. Okay, now, exoplanets is all dominated by transits. And that means you have the planet goes in front of the star and you see a little dimming in the brightness of the star. So that's how you can very easily discover planets, and you can actually measure their radii doing it. And I talked a lot about there's stuff going around the white dwarfs, and you might think, well, if you have the right inclination, some of that stuff should pass in front of the white dwarf and cause transits. And indeed, the Kepler mission was great to find exoplanets, but Andrew van der Burg found transits in the light curve of a white dwarf, WD 1145 for short, recurring with a period of 4.5 hours. Now, 4.5 hours is, if you use Kepler's third law, you know the mass of the white dwarf. That is the distance at which a rocky body will start to fragment because of tides. So it's perfect, it's textbook. It was kind of, you would have predicted 4.5 hours, but this was actually first discovered, and then people said, yes, that makes total sense. Here, the Kepler light curves, they're not very impressive. And then spectroscopy showed it has metals in the atmosphere, so it's accreting. It has an infrared excess. There's a dust disk, makes all sense. This is one of those systems that we look edge on. And so we started to obtain high-speed photometry from telescope in Thailand. About half a year later, or a couple of months after the discovery, this is one of the 4.5-hour cycles of the debris going around the white dwarf. And to our big surprise, we didn't see one transit, but there's multiple transits. It's actually hard to say where there's not some absorption going on, and its deep is up to 50%. Now, modeling some of these narrow features, we can put some limit on the size of whatever is blocking the light of the white dwarf, and it turned out to be of the order a few white dwarf radii. So what we see is not asteroids going in front of the white dwarf, and they would only cause very small dips because they're very small compared to the radius of the white dwarf. What we see is clouds of dust. Okay, so what we think happens is that you have solid bodies, fragments, rocks, boulders, asteroids going around the white dwarf at a period of 4.5 hours. And for whatever reason, occasionally, let me just call it activate, and they eject gas and dust, and those gas and dust clouds move out, and cover the white dwarf. Now, again, curiosity is very exciting. Let's move on and observe the same star continuously for a couple of nights. And so we had multi-site photometry so that we can observe non-stop as the sun rises above one telescope. We move to the next one. The data here, that's from the INT, and the blue data is from McDonald Observatory. This is a couple of nights from end of January until beginning of February. And it's folded on the 4.5-hour period. So every location on this axis corresponds to a fixed position in azimuth around the star. Now what you can see is that there are features where you see absorption starting shallow, narrow at the beginning. So that's a dust cloud coming out of a fragment at this location around the white dwarf. It gets deeper and then it widens and it becomes shallow again. And so that's the dust cloud being ejected from a fragment, becoming bigger and then spreading an azimuth. What we can do with this type of data is we can measure very, very accurately the time, the timing of these transits, and we can determine the orbital period. So there's a fragment here, there's a fragment here, there's a fragment here, and so on. And so we can track those over long periods of time. And that's what we did for a bunch of them. And we found that all these fragments have periods identical to within a few seconds. And so now you think, well, this sounds or looks like a ring of debris around the white dwarf, lots and lots of fragments, and all of them kind of start to eject dust at some point and then calm down again. And these periods are stable over hundreds of orbital cycles, so hundreds of the 4.5-hour cycles. Now we have dynamical data, and we can then say we go in and do n-body simulations to model this system. So this is all the observational data. And we then went in and said, okay, we use a n-body code and we place an asteroid, which is made of 5,000 particles with a given density around the white dwarf at the position where the material is. And we see what gravity will do to that body. So this is 5,000 particles held together only by its own gravity. There's no internal strength. They're not stuck together. It's just the body holding itself together by its internal gravity. And we did two tests. We said, let's assume we have homogeneous density. So all the body throughout has the same density, 2.5 grams per cubic centimeter, or a differentiated body where you have lighter material at the surface and denser in the core. And the average density is 3.5. 3.5 grams per cubic centimeter is roughly the density of rock. And I'll switch on movies. I'll try to start them both at the same time so that you can see what happens. And it was very interesting. So the differentiated body spits out particles at a very gentle, slow rate, whereas the homogeneous body disrupts. And we're like, oh, well, that's interesting. It is actually, if you study binary stars, you know why. Because the density at which a body fills its Roche lobe and starts fragmenting is only a function, the orbital period at which the body will fill its Roche lobe and start fragmenting is only a density, only a function of its density. So if we have a differentiated body, the surface layer have a lower density. We peel them off. And that means the average density goes a little bit up. And that means the body has to move a little bit further in to keep filling its Roche lobe. So having a gradient in density stabilizes the process. Whereas if you have a homogeneous body, it kind of leads very quickly to catastrophic disruption. Okay, right, so we can actually place some interesting constraints on the total mass, less than 10 to the 20 kilograms, which is size of a large asteroid, and a density of about 3.5, which corresponds to rock, and it has to be on a circular orbit. You can't have an eccentricity, and it is differentiated. Right, so there's so much more going on in this system, and I just show you here light curves obtained in Thailand, and you will notice a theme throughout my talk. Is a lot of this is curiosity driven because we really don't know what happens in these systems. So we said, well, we see transits evolving over nights. What happens over years? So that's data obtained over 8 years. And you see that the transits that I showed you initially start to become weaker and disappear. If we observe the star today, we wouldn't know that they're transits. Well, we're lucky. That means whatever happened to the system, either all the fragments and bodies have disappeared and ground up into dust, or whatever caused them to activate has stopped. And so they're no longer ejecting dust, but they're kind of invisibly orbiting the star. Right. So this was one star. You always want, if you find something new, you want to have a sample, a class, so you can study the different properties, parameters, and so on. So the search was on for transiting white dwarfs. Here's a light curve. You may look at it and say, looks exactly the same as WD 1145. Asymmetric, deep transits. The time scale is totally different. This is 110 days. So we think there's probably, this is in an early phase where you have a body coming in on a highly eccentric orbit initially from maybe an AU to AU. It starts to disrupt, it transits, it goes out again, and then comes back after 110 days. And again, these transits, they repeat over years. This is a third system, and there's a very recent paper where we took the data from all the photometric surveys. So we used CRTS, Assassin, Atlas, and ZTF. And we stitched them all together and cross-calibrated because they're in different bands and it's a bit painful. But if we do that, we find this white dwarf here, which shows transits today, had a very long phase, couple of years around 2011 to 2015, where the system dimmed by 0.1, 0.2 magnitudes overall. And so we think, well, probably back then, there was some catastrophic collision, something happened that generated a very large amount of dust that dimmed the star. The dust slowly dispersed, and today we see whatever is the aftermath of that. And then just, this is the last example, just to show you that they're all different, the ones that we found so far. This system, again, this is about 20 years of data, has little fading episodes every couple of months, about 2, 3 per year. And we obtained high-speed photometry on 3 occasions. And what we found is that when the system is bright, we don't see any transits, no activity, it's a flat light curve. Whereas if it's in one of those faint states, we see very large activity. Now, if in my old days, I would have said this is a cataclysmic variable and it's actually flickering disk. But this is absorption. There's no emission coming up, additional emission. This is all absorption. And so the cartoon we have in mind is that we have a highly eccentric orbit of the body that it initially had. It went around the white dwarf a couple of times and started to fragment. And then you have these kind of clumps of small fragments that pass in front of the white dwarf. And when one of them passes in front of the white dwarf, you get this very short-term variability of absorption. And then there's a bit where there's nothing. And the star becomes bright, flat light curve, and then comes the next clump. And we haven't figured out the periods of these clumps around the orbit. Okay, so I hope I convinced you that there's a lot of stuff going around going on around white dwarfs. So there's all kinds of things that are related to material, asteroids, usually small bodies, fragments of planets. And now I come to the question, how do we actually measure abundances of planets? And again, this is where you can participate if you want, but if you don't want, that's also fine. How do we measure the composition of planets? And I have a few hints up there, so you just need to read it off. So we can send astronauts to the moon, take moon rocks that will tell us something about the surface of the moon. We can, of course, analyze the composition of the surface of the Earth. We can drill maybe 10 kilometers into the Earth. We have lava that gets ejected, and that tells us something about layers a little bit deeper. We can go to Mars. We can fly through the geysers of Europa. All of this tells us just the abundances of the very outer layers of the planet. The way that planetary scientists, solar system scientists, determine the overall abundance of planets is using meteoroids. Meteoroids are fragments of disrupted planets like the asteroid belt. And some meteoroids, they're still hanging around from the formation of the sun, from the protoplanetary disk. They haven't changed at all in 4.5 billion years. And so by collecting meteoroids, analyzing them in the lab, and working out, is this a fragment of something that formed as a planet? Yes, because it's a pure iron meteoroid. So that is actually, that used to be in the core of a differentiated planet. Whereas this one here might be one of those primordial asteroids that formed from the original material 4.5 billion years ago without going any change. you can work out the composition of the material that was used to form planets, and then you do planet formation models, and you need to reproduce with the ingredients you have the properties of the planets we see, which means mass and radius and bulk density. Okay, so now we use white dwarfs to do exactly the same. We have the white dwarf, which has a hydrogen-helium atmosphere. We have meteoroids, fragments. They fall into the white dwarf. We take a spectrum. We measure the abundances. We can then infer what was that body that fell into the white dwarf made out of. And I'll show you two examples. And again, without going into any details on model atmospheres and atomic data and any of that. I just show you two spectra of white dwarfs, which have pretty much the same properties. They're relatively cool, 5,000–6,000 degrees. So they're about 1.5 billion years old in terms of cooling age. But they look very, very different. So the top spectrum, you see absorption lines from calcium, sodium, tiny amount of iron, titanium, and calcium again. Whereas the bottom one has pretty much only iron and nickel lines. Now, what does that tell us? It tells us that the white dwarf at the top has ingested a planetary body that is rich in crust elements, because in the crust of the Earth, we find sodium, calcium, titanium. Iron, because it's heavy, when the planet forms, it sinks into the core. So we don't have much iron in the crust of the Earth. Whereas if you accrete a fragment of a planetary core, it will be rich in iron and nickel. Okay, so we can actually tell that these two white dwarfs have accreted different types of planetary bodies, fragments, crust and a core. Now here's a really nice table that Beth Klein put together in a paper in 21, which lists the year when an element was for the first time discovered in a spectrum of a white dwarf associated with accretion of planets. And you have 1917, calcium, and then 2021, beryllium. And putting those into a periodic table, all the elements that have purple rings around it have been detected in white dwarfs. And so we can start to build up some knowledge about the composition of rocky bodies that were once going around main sequence stars. And again, just showing here an example because I find that amazing. So if you are into stellar abundances, lithium is a very difficult element to detect. These are 3 white dwarfs that have lithium lines. Now, lithium burns in stars, so this lithium can't be from the primordial star. Well, it couldn't anyway because everything sinks into the core. But these stars have accreted lithium from crust elements. And if you're a little bit more bold, you would say it's oceanic crust if you look at the potassium to lithium abundances. Okay, so we can do this, and then we can say we have all these abundances measured for white dwarfs. How does that compare to the solar system, to what we know in the solar system? And this diagram is a little bit difficult to interpret, but it's actually quite easy. What I have here on the x-axis is the different elements: carbon, oxygen, sulfur, manganese, and so on. And on the y-axis, I normalize the ratio of each element here to that of silicon. The reason I do that is that measuring absolute abundance is very difficult and relative abundance is much more precise. And then I divide by the same ratio in the bulk Earth, average composition of the Earth. And very simply speaking, things that are above that line are enhanced with respect to the average Earth composition. Things that are below are depleted. Okay, so then we can start to compare. And what we find so far is that pretty much every white dwarf we analyze is more or less consistent with rocky bodies in the inner solar system. Right, last part, I will talk about actual real planets, because everything I mentioned so far, people say it's an asteroid, maybe it could be a shredded moon, but it's small fragments. We're not talking about planets here, but now we will talk about planets. As I said, transits. You find planets doing transit searches, and of course, Tess and Kepler have been fantastic missions, and then Andrew van der Broek, again, same guy as with WD 1145, found a transiting planet around a white dwarf, 50% depth. How does he know that this is a planet? The team obtained Spitzer light curves at 4.5 micron. The transit looks exactly the same depth, same shape. So the body is basically invisible black going around the white dwarf. It must be very cool. We see no emission from the orbit object that transits the white dwarf. And the constraints are period is, and now pay attention, 1.4 days. I'll come back to that in a second. And the mass limit was something like around 10 Jupiter masses or so. So just about borderline low mass white, low mass brown dwarf, or high mass giant planet was the constraint they could get. Why is 1.4 days interesting? A planet that goes around with 1.4 days would have been very, very deep inside the red giant envelope. So it shouldn't be there because it would have been evaporated. So that planet must have migrated inwards after the white dwarf was formed. And that means it's probably a multi-planet system and there's planet-planet interactions. And this planet happened to be migrating inwards because of gravitational interaction with other planets. There's lots of papers that explain how the planet might migrate inwards. It's interesting. It's a very cool white dwarf. It doesn't have any metals in the atmosphere. There's no debris disk because the planet is still intact going around the white dwarf, and it's a giant planet. So this is a boring white dwarf. Nobody would have studied that for any reason. It just came out of the transit survey, and it's very nearby. I come back to that also. And then you can do what exoplanet people do for a living, that is transit spectroscopy. So you can measure the radius of the planet at different wavelengths. And that will tell you something about the composition of the atmosphere if it has one. And this is the spectrum from Alonso et al. And it's very flat. And the main constraint was that they can narrow down on the mass. So it's less than 2.4 Jupiter masses. And I think there's James Webb programs that will do transit spectroscopy of this system, again, with the hope to detect some more information about what this planet, if it has an atmosphere, and so on. Second property, so this is so for the only transiting planet. Second method is microlensing. So we are here and we observe some background stars, and then there's some object that has a mass passing in front through our line of sight. When the object is just along the line of sight, we get gravitational lensing. That means we get some of the light that would otherwise pass beyond the Earth, focused on the Earth, and so the background star gets brighter for some short period of time. And microlensing is very nice to find, for example, isolated black holes drifting in across the sight line. Now there's this microlensing event published by Blackman, which has multiple brightenings, and we can't see the lens, we can't see the object that crosses the sight line. And from all the constraints, they say, well, the object has about half a solar mass, which would be maybe a K star, but at the distance they estimate, they would detect a K dwarf. So they can't detect anything. They say the only other object that has half a solar mass, but is invisible because it's so faint, is a cool white dwarf. And from modeling the microlensing light curve, they found that there is planet, and the planet has an orbital separation of several AU, which is nice because this is where it would survive the red giant phase, and it has a mass of about a Jupiter mass. So we see here a Jupiter at about Jupiter-like distance going around an old white dwarf very far away. Unfortunately, you can't do anything with this because it's a one-off. Once the lens passes in front of you, that's it. It will never come back, and it's too far away to do anything with it. Common proper motion. Well, you look for stars that move in the same direction. That's what the name says. This was actually the first planet mass object identified. There's the white dwarf here, and there is a very faint object in the infrared. There's a Spitzer imaging and both of them have the same proper motion. So they move in the same direction. They're gravitationally bound. And if you look at the parameters, the white dwarf is nearby, cool, 20 parsec, nothing special about it. And the separation is now 2,500 AU. And the temperature is around 300 Kelvin. The mass is around 7 Jupiter masses. Now that's very interesting, again, because at 2,500 AU, a giant planet couldn't fall initially. So what we think might have happened here is, again, gravitational interactions, multi-planet system, and this planet got ejected. Rather than being pushed inwards, it got pushed outwards, and so it's moving away from its host star, but it's still keeping the original proper motion, and has by now separated from its host star by those 2,500 AU. And then evaporation. Evaporation is a big thing in mainstream exoplanets. Here's a gas disk. So I told you, you see a double peak line profile. You know there's a disk around the star, and we detected this star, and we found that it has emission lines of oxygen, hydrogen, and sulfur. So it's no radial velocity changes, not a binary star. And we detect oxygen and sulfur in the hydrogen atmosphere of the white dwarf. So there's a disk of volatiles, and those volatiles accrete onto the white dwarf now. That was a bit of a hard puzzle. Measuring the abundances, we find that this is now normalized to oxygen, irrelevant detail. Hydrogen and sulfur are enhanced by quite a bit with respect to the Earth. They're not far off solar abundances. And all the heavy elements that we see in those rocky bodies, calcium, magnesium, iron, they're depleted by up to a factor 100,000 with respect to bulk Earth. So that means it's a pure gas disk. That caused some head scratching until I came across this figure in a handbook on solar system abundances, and I looked at that Uranus and Neptune. I thought, we have hydrogen sulfide and we have water, and this is the three elements we see. And then there's other stuff, methane and well, forgot what NH4 is, but we can't detect nitrogen or carbon in the optical spectrum of that star. It's like carbon, nitrogen don't have good lines in the optical to be detected. And so we think we have an evaporating planet going around the star. Now, to evaporate a planet, you need a lot of high energy photons that hit the surface and deposit kinetic energy so that you drive an outflow of material. And that only depends on the number of extreme ultraviolet photons, so beyond the Lyman limit. Now, the white dwarf has a temperature of 27,000 degrees, and pretty much all its photons are beyond the Lyman limit. So it has a very high EUV luminosity. And we modeled this as a giant planet at around 10 solar radii. So the orbital period would be about, say, 2 weeks, going around this very hot white dwarf. And it leads to evaporation. And the evaporated material, we see that forming a disk and then accreting onto the white dwarf. Okay, next method is astrometry. There's a very large potential that Gaia has, because in addition to radial velocity wobbles, if you have a planet going around a star, well, actually both go around the center of mass, and that means the star will have a little perturbation of its position on the sky, an astrometric perturbation. And Gaia has sufficient precision to detect white dwarfs that have giant planets because of that astrometric wobble. And in the data release 3, they actually released a planet candidate at a distance of only 9 parsec with a period of 33 days and a mass of 9 Jupiter masses. So everybody in the field was going like, wow, that's it. That's a proper detection of a planet. And there were follow-up proposals. There's James Webb is looking at that and so on. And then the Gaia team silently withdrew that planet, not in an erratum, but in a little note on their news website. So as of now, we don't know what happened, but they now say there was a processing error and that planet no longer exists, but it has metals in the atmosphere. So there's follow-up data coming, and I don't think the story is yet quite finished on this particular, but it's a method that should work and will work with more Gaia data. Final method is direct imaging. So you take an image, and if you do that with main sequence stars, the main sequence stars are so bright that the contrast ratio between the star and the planet is like 10 to the 8, 10 to the 9. And usually you need a coronagraph. You block the light from the main sequence star to pick up a signal from the much, much fainter planet. Now, white dwarfs, they're themselves very, very faint. And the contrast ratio between a hypothetical planet and the white dwarf is such that you don't need any fancy coronography or not. You just go into the infrared where the white dwarf is very faint. Now, you can do that with James Webb these days. And there's several planet candidates out there. And you see here MIRI images. That's the white dwarf. That's the raw image, or the calibrated image, but as it is. And then here, the white dwarf has been subtracted. So the star shows where the white dwarf is on that image. And you see there's some faint smudges. And then this is the image where also the planet candidate has been subtracted. So the planet candidate is this blob here and this blob there. And this is some background object. Now, the paper doesn't say these are planets, because there's, of course, the chance that these things are background objects. They have the right color to be a planet, and they have the right magnitude to be a planet. But it could still be a coincidence that it's a background redshifted small galaxy that has basically point shaped, that happens to be sufficiently close to the white dwarf. And what needs to be done is to reobserve those stars in a year or 2 or 3, because these things, they have quite high proper motions, the white dwarfs. And then, just as I explained the common proper motion studies, if these are actual planets, the white dwarf in a year or 2 might be here. This thing will move with it. And if you wait long enough, you would actually see the orbital motion of the planet around the white dwarf. So if you have 10 or 20 years baseline, you could see real planets going around real white dwarfs in real time. Right, quick summary. So currently there's 6 good planet candidates. With every single one, you could argue for some reason that maybe it's not a planet, maybe it's a brown dwarf, maybe the photo evaporation is something else, you just don't know what's going on. Maybe these are background objects, but they won't be all wrong. And 4 out of these 6 are within 25 parsec. Now, within 25 parsec, there's only 300 white dwarfs. And this is very hard. These are very hard things to measure. So transits, you need the right geometry. James Webb imaging is very expensive, so only a few white dwarfs have been observed. Most of the white dwarfs here are too cool to photo evaporate anything, and you need a planet on a very short orbit, and so on and so on. So the short summary is that it is very likely that actually giant planets, we're not talking yet about Earth-sized planets, but giant planets around white dwarfs are probably quite common. And in the years to come, especially with James Webb and Gaia, this number will very likely go up. And so that brings me to my last slide, which is a very brief summary. So planetary systems of some type are very common, and I would say they're as common as planetary systems around main sequence stars, which isn't a crazy idea, because the solar system will have remnants of the planet of the solar system, like fractions of the solar systems will orbit a white dwarf. And many more will be discovered, and they're very exciting. We still have so much to learn, especially about the tidal disruption processes, but they're also extremely good because we can measure the abundances of rocky bodies and also of planet atmospheres in the case of that evaporating star. And they give us insight into the architectures of planets around A and F type stars, because that's your typical white dwarf that you see today would have been in the past an A or F type stars, because G stars live so long that only few of them have already turned into white dwarfs. And I will stop here. Thank you very much.
So thank you very much, Boris, for the very interesting talk. Do we have questions or comments?
I have 2 questions. Very nice talk. The first one is, you have shown a couple of spectra in which you have in one of them there is a lot of iron. Does this mean that possibly, let's say, like a relict Earth was still existing around the white dwarf, the nucleus of the Earth, I mean basically iron, and this is the kind of signal that you might detect of the death of our planet, or the death would completely disappear? And the second, well, if you want to answer.
Let's deal first with the first question. Yeah, that's a difficult question. So yes, hypothetically, you could say the Earth has an iron core, and maybe during the red giant phase, you have a red giant wind, you have a very strong, very large luminosity. You could maybe erode off crust and mantle and then be left with the iron core. And then if you see a white dwarf that accretes mainly iron and nickel, that could be the core of an Earth-like planet. But it could also be that there was a collision between planetary bodies, and at least one of them was differentiated, had an iron core, and it's a fragment of that iron core. So that's why I said meteorites are so useful. We have pure iron meteorites that fall onto the Earth. And so that tells us that out there in our solar system, there were bodies that were large enough to form an iron core, but then something bad happened to them and they broke up again. So there's planet cores in our solar system, planets that didn't make it to today.
Okay, so they can be also from the iron meteorites from the from the asteroid belt
Yes.
that
Yes.
fall inside the
Yes.
white dwarf because of different alterations.
Yeah.
And the other question that I have thought of it on several occasions, what would happen with the interaction of the eventual planets with the planetary nebula that is formed when the system collapsed?
Yeah. So that's a question that actually has been asked a lot in the past when people actually had doubts that what we see has anything to do with the creation of planets. Some of it may just be remnants of planetary nebula. The density of the outflowing wind from red giants is relatively low. And so it may erode the surface. It will probably strip atmospheres of close-in rocky planets. So even if the Earth survives, because it moved a little bit out, the wind and evaporation would strip the atmosphere. But then the planetary nebula is much, much larger in size than the planetary system inside. And so for a short period of time, you would have remnants of a planetary system, and then further out, you would have the planetary nebula. And then with time, the white dwarf and the gravitational bound planets, they move through space, and the planetary nebula gets left behind. It dissolves into space. Not much, no. So with the red giant wind that goes past the planets, yes, but with the planetary nebula, probably not so much.
Hey, Boris, nice talk. I'm wondering if it's a bit of a surprise that you have so few planetary candidates in the direct imaging results, given that you see a lot of stuff very close to white dwarfs. So you must have stuff out there kicking stuff in, I guess. And therefore, is that actually a surprise, or is that just an artifact of the magnitude limit of the direct imaging observations?
You mean the James Webb images that
Yeah.
I showed?
Yeah, that one of the last slides you showed.
I'm not so I think it's actually, I would say it's the opposite. I think it's in this specific paper, they detected planet candidates around 2 of 9 systems that they observed. And so it's a fairly large fraction because those must be giant planets that are sufficiently warm to be detected by James Webb. And these are probably several Jupiter masses. Of course, many white dwarfs could have Neptunes or super Earths and so on, but we wouldn't be able to detect those even with James Webb. To me, the key question is, can we confirm that those things are actually giant planets? And will people study, say, 30, 40 white dwarfs and put statistical constraints on the number of giant planets and the mass or temperature distribution in the next 5 years or so?
Any more questions or comments? I don't see any, and I don't see any online, I think, either. So thanks again, Boris, for the very exciting talk and very exciting prospects as well. Thank you. Have the scientific coffee right now, so you can go to have some coffee with Boris and discuss with him more details.
Oh, that would be the end of us, but not the end of the world. Yeah. Okay, let me make sure that I give you back all your. Yes. Okay, yeah, thank you. So this we only found around 1 or 2%. That's sensitivity because we are mainly sensitive to optically thick this dust is, where you pretty much fill all the entire brush lobe with dust. But I think
or there's information for planets and so on.
So probably I didn't make that clear. It's a very short temporal period. So the disk forms, and then over maybe a million of years, it accretes onto the white dwarf, and then it's gone. Yes, yes. And you may have another body coming in around the same white dwarf 20 million years later. But it's episodic. Yes, yes, yeah. So the fact that we see disks around about no, most of the disks are probably small bodies, asteroid size. Yeah. The real planet size. Yes. Yes. Yeah. 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 So planets, we are still in the beginning.